Computational fluid dynamics is one of the most computationally expensive problems in science. Simulating three-dimensional turbulent flows around complex geometries at moderate to high Reynolds numbers can tie up supercomputers for days. Machine learning promises to cut that time down to milliseconds by training neural surrogates on high-fidelity simulation data. But here's the catch. The field is starving for validated, standardized datasets. Most public turbulence databases focus on simple, canonical flows. Real engineering problems involve complex obstacles, and without rigorous physical benchmarks, it's impossible to fairly compare neural operators. That's exactly what this new research addresses. The team at FAU Erlangen-Nürnberg has built a fully reproducible pipeline that generates training data for 3D channel flows around procedurally generated geometries. Reynolds numbers range from 1,000 to 10,000. They start with primitive shapes like cylinders, spheres, and wedges, generate geometric variations, and run Lattice Boltzmann simulations. The output isn't just raw numbers. It's structured HDF5 datasets containing time-averaged fields, consecutive velocity snapshots, force coefficients, and spatial occupancy masks. Everything is scaled and ready for neural network training. Let's talk about the solver itself, because the physics accuracy here is non-negotiable. They're using the waLBerla framework, which provides highly optimized, code-generated Lattice Boltzmann implementations. The core is a D3Q27 stencil with a cumulant collision operator. If you're familiar with moment-based multiple relaxation time models, cumulant-based approaches offer superior numerical stability and accuracy, especially in turbulent regimes. They also implement a fourth-order advection diffusion correction scheme to handle the energy cascade without blowing up. Interestingly, they tested explicit subgrid scale models like Smagorinsky closures, and adding them actually degraded physical accuracy. The inherent controlled dissipation of the cumulant approach is enough. For boundaries, they use a quadratic bounce-back scheme, which gives second-order spatial accuracy at the cost of computing wall distances, but it's critical for capturing accurate separation and weight dynamics. And validation is where this pipeline really earns its keep. They didn't just check if the numbers look right. They benchmarked against experimental data for flow around a sphere at Ray 1000. The Lattice Boltzmann setup matches the Strouhal number at roughly 0.18, confirming correct vortex shedding. The recirculation bubble length aligns with experimental measurements. Streamwise turbulent intensity shows the exact same dual-peak structure downstream of the obstacle. Even instantaneous snapshots capture hairpin vortices with identifiable heads and trailing legs. They also ran grid convergence studies on drag coefficients across resolutions up to 1024 by 512 by 512, matching classical experimental references within 6%. This isn't just a dataset. It's a rigorously verified physical benchmark. Now, what happens when you throw neural networks at this data? They tested a few baseline architectures for predicting the mean streamwise velocity field from a binary geometry mask. You've got the original Fourier Neural Operator, a factorized version, a hybrid, and a standard 3D UNet. The UNet clearly outperforms the Fourier-based models on accuracy metrics like normalized root mean square error and mean absolute percentage error, while also maintaining a competitive throughput of over 30 samples per second on an A100. The FNOs struggle with the spectral bias problem, oversmoothing the fine-scale turbulent structures, while the convolutional UNet naturally preserves local flow features better at this resolution. So what's next? The roadmap focuses on systematic benchmarking across multiple prediction tasks, next time-step forecasting, super-resolution from low-res snapshots, and drag coefficient extraction. A major focus is tackling spectral bias. They plan to experiment with expanded loss functions that combine standard L2 losses with adversarial and spectral components, following recent work on learning turbulent flows. They're also exploring attention mechanisms, both as channel and spatial gates in time-conditioned UNets, and as linear attention coupling in Fourier operators. And crucially, they will measure computational cost directly, comparing the wall clock time and memory footprint of these highly optimized LBM solvers against neural surrogates to answer the real question: when does the AI actually become faster than the physics? I should be transparent about the current limitations. Generating high-resolution turbulent data at this scale demands serious compute and storage. The pipeline is currently optimized for the transitional to turbulent regime between Ray 1000 and 10,000. The baseline model results are proof-of-concept level and haven't undergone exhaustive hyperparameter tuning or variance estimation. But that's exactly why they're releasing this work in progress to the community. They're looking for feedback on the validation methodology, the planned benchmark suite, and what evaluation priorities matter most for neural operators in turbulence. This pipeline isn't just a dataset. It's a building block for hybrid differentiable solvers and physics-informed machine learning. If you're working on scientific machine learning, fluid dynamics, or neural operators, this is a framework worth watching. Let me know in the comments which architecture you think will finally crack reliable long-term turbulent forecasting, and I'll see you in the next one.